So we've established that the sun emits an enormous amount of energy, but the earth does not absorb all of that energy because the Earth's atmosphere absorbs quite a bit of the ultraviolet energy from the sun, right in here. So this is the ultraviolet energy from the sun, and I placed this as best I could. This is the area, the wavelength that the atmosphere will absorb in UV. So you see this right around 0.1 to 0.3, and you see it absorbed in purple, full absorption, almost 100% of UVA and UVB ultraviolet radiation. There is some that gets through between 0.3 and 0.4 nanometers of wavelength. And that's what you protect against with sunscreen. And you see here that there's very little absorption by the Earth's atmosphere or by clouds in the visible wavelengths put out by the sun. So we in our Earth's system absorb mostly visible energy. When it comes to the longer wavelengths in the infrared that start at about 0.8 or 1.0 nanometers and go to about 5 nanometers, we are seeing quite a bit of absorption by the atmosphere in those areas. The purple relates the percentage of energy absorbed. So you see here that it is irregular, but it is significant for the Earth's atmosphere. This is important because that means that the Earth absorbs less energy than the sun puts out, and then the Earth's system needs to emit as much energy as it absorbs to stay in radiative balance. Well, there is a beautiful design to the Earth's atmosphere. And the beautiful design, which is just stunning to really study, is the fact that we have very low absorption in this visible ray area, which allows our eyes to be optimized through evolution to see these beautiful colors. And that is called an atmospheric window. It allows visible light in to our Earth. There is another window that allows our Earth emissions infrared to get out and vent the Earth. And that other window is in here in the far infrared area. So in other words, the far infrared area is way down in the longer wavelengths. We emit, as the Earth's black body curve, we emit in that area of the long wave radiation for far infrared. And as we emit, we have this beautiful vent here that allows our emissions to go straight out back to space. And that is the infrared atmospheric window. This is the visible window. This is the infrared atmospheric window. Now you might say it's not perfect because there is some absorption in here. And that absorption does play a role in ping-ponging our infrared back and forth and maintaining the warmth of our atmosphere. But in general, this is a nice low window for allowing our Earth to vent our wavelengths of energy that can equal the wavelengths that we absorbed. A very important point about the atmospheric window. Now let's talk about the atmosphere and its absorption and its emission, because we know that it's not a perfect absorber. It's a selective absorber of certain wavelengths due to the greenhouse gases. But can it also emit as much as it absorbs? Well, let's look into what it really absorbs. We had said that of the 100 units of solar energy coming in, there are 19 units that are absorbed by the atmosphere and the greenhouse gases and the clouds, which contain the most voluminous greenhouse gas, water vapor. And in absorbing that 19 units, the atmosphere must emit those 19 units. It must emit the same total energy measure as it took in, but it took in a lot of high power UV. So that means when it emits IR, it is going to have to emit more IR. So here's the 19 units that were absorbed by the atmosphere. And it absorbed high power UV along with IR. It then turns around and emits more IR in order to equilibrate the total energy between the high power UV and the lower power IR. It emits more IR, and therefore that IR will now go out to space. So these purple boxes are the atmospheric balance of what it took in high power UV and IR, and what it put out in IR only in greater amounts. As a result of all of this, we can say that our Earth system is in a state of radiative equilibrium. Our system of our surface and our atmosphere does absorb and emit in equal amounts of total energy. And that means that we have a net gain of 0 energy units. And this is what all systems in the universe will tend to, an equilibrium of energy. Now, is our radiative equilibrium a sign of a black body for the Earth's system? Well, as we know, the Earth's surface is a black body, but the Earth's atmosphere is not a perfect black body. It does emit as much as it absorbs, but in doing so, it ping-pongs a lot of that energy back and forth, back down to the Earth's surface. If it were a perfect black body, it would absorb and then emit directly out to space, but that is not the case. So we have radiative equilibrium in the Earth's system, and we have a component of a black body in the Earth's surface, but we do not have a perfect black body in the Earth's atmosphere. And as a result of that, we have life on Earth because we have warmth and we have liquid water. I hope that helps you out. I'll see you on the next video.